So we're going to be doing Fleury's algorithm for Elucidiean circuits, and also the other one, Helzer-Boyer's algorithm. So for the Fleury's algorithm, we need to see, the first condition that we need to see is, do we have any odd vertices, right? So do we have the degree as odd? The degree should be odd. So the degree of W is over here is 2, for U is 2, 2, 2, and for V is 2, and for X is 2, and for Z that's also 2, and for X would be 1, 2, 3, 4. X would be 4, and Y would be also 4. So we don't have any vertex, any two vertices. We exactly need two vertices which should be odd, and we don't have that in this case. So we can take any vertex of our choice and use that as a starting point. So we're going to take V, and for this algorithm I'm going to just redraw the graph very quickly. Right. Okay, so the way how this works is, whoops, there we go. Okay, the way how it works is, we start with V and we make a connection from V to X, and we need to make sure that there's a path. There is wait, right? So the reason why we've drawn another graph is because it's just going to help us see which are the remaining paths that you can take back to getting back to V. So from V to X, you go here and you said, okay, I'm gonna go from V to X, so you remove this path. Okay, so now now you can take any path you want. So let's say I go from X to Y, let's say that's 2, so this is gone, and I go from Y to back to X, so go back up and we remove this. Then we can say we can go from X to Z, so X to Z, and then from Z oops, so that's 3, that's 4, and then from Z we can go back to Y, so that's 4, remove this, or 5 basically, and then from Y to we go back, and that's 6, then to U, that's 7, U to 2, that's 8, and then 9. So in basically 9 steps we can traverse the entire graph such that we are getting back to our starting point, which is V. And the simple thing is, you don't even need to like redraw the entire graph again. You can just do this based on intuition, that you just have to traverse in a way in which no edges are repeated and the vertices can be repeated. Now the other method is a better approach, because it ensures that only Elucidiean circuits can be it only works on Elucidiean circuits. It doesn't work on semi-Elucidiean, which means that it will only work if there is every vertex has an even degree. So I'm just going to redraw the graph very quickly. So we have V, I think this was W, this was U, something like that, and then we had X, Y, and Z over here, and then this was making that, and then this was, I think that was it. Yeah, that was it. Okay, so now the way how this algorithm works is, we need to make sure that every vertex has an even degree, so which we've already proved. So this is 4, sorry, this was 2, that was 2, that was 4, that was 4, and that was 2. So we can take any vertex and we're gonna take V again. Now we need to create a very, very, very simple circuit. So for in this case, I would say C1 would be VW UV. So this. Okay, very simple. Now we have to see which of the edges, are there any edges that we haven't used yet. Okay, So when we look at this, when we take this example, we see that W and U cannot have any other edges connected to the other graph, right? Which means that this is not a good guess. We need to take another guess. So let's take V, X, Y, and Z. So C1 is V, X, Y, and V. So basically I'm saying V, X, Y, and back to V. This is a good guess because you can see that X is now connected to Z and Y is also connected to Z, and we can traverse to the other edges as well, because we need to make sure that if there are any vertices, we can basically see other paths over here. So C2 is then going to be, so now we have done this part, then we're going to do it for X. Let's say we're choosing the vertex X. So X is going to be X, Z. So I'm doing X to Z, then Z to Y, and then this, right? So X to Z, Z to Y, Z to Y, and then Y to back to X. Okay, and then there's this circuit. So I can just take this and I can place that over there. So this will then become C1 equals to V, and placing that, so Z, Y, X, Y, V. So V, wait,